I've started.
Hello, good morning. Welcome to our class. Please let me know if you can hear me so that we can begin.
Yeah, we can hear you very well.
Thank you. So let me start by, as we wait for people, I see only 80 people here. Let me start by giving a couple of stories. I'll call them stories. When I started teaching this course in 2017, I think. This class had over 100 people retaking, okay? So over the years, I've tried to reduce this number by teaching in a way that brings in everyone and gives them a chance. And a lot of people have managed to finish their retakes. Maybe every year now I give about 20 retakes, okay? And I'm really telling the people doing this course for the first time, the first years and second years of computer, that you can easily fail a very simple course like this one. And when you fail it, the next time you do it, it's just harder to pass it. So you'll find people who are from 15, you know, their registration numbers have 14, 15, 16. Recently, I had somebody with 10, somebody who started in 2010. Eventually, she finished. So I'm basically warning you to take this class seriously. Two, we have formed groups, and I worked with I think Jesse mainly to make these groups. And once we finished making groups, people started sending me texts and emails that they had not got groups and that they submitted their names but didn't get groups. Look, you're supposed to make a group and submit it to the class rep. The class representative is not there to form for you a group or to make sure you have a group. He's not your worker, really. So it is your responsibility to make sure that you have a group. And since there was a deadline, it means that if you didn't have a group by the deadline, then you simply don't have a group. Now, I've given you a group assignment. Please start working on it immediately. I think I gave it a couple of weeks for you to submit. After that group assignment, I'm going to open up forming groups again. So people who don't have groups will have another chance to form groups then. But this homeworks, essentially what I'm trying to say is that you cannot do this, this assignment one. I would advise you to do it anyway. You just can't submit it because I want to grade it anyway. So I've seen that there is a bit of unseriousness. If I tell you to form groups and you're not bothered really, I mean, why am I here then? Why am I even wasting my time teaching you? Another thing that I might do is stop giving you my recordings. So I encourage you to be attending class so that you can learn in class. If you don't attend class, you might have to read things on your own. As you know, I told you at the beginning, I'm not obligated to give you my recordings, and I'm happy to do that, but only if I see complete seriousness on your part. Okay, so having said that, today we are starting a new chapter, chapter 4, called Combinational Logic Circuits. Combinational logic circuits essentially combine the gates that we have been looking at in a way that achieves a certain goal. So maybe we have some scenario we want to design, and so we combine gates in such a way that we can design that scenario. I'm going to give you an example. In fact, this is not the first time we are going to see combinational logic circuits. So every time you combine a number of gates, you are creating a combinational logic circuit. And we've already seen this with like, I think we did the car ignition, and if the driver is present, you start the car, and it, you know, I think it is is it the door open, then something happens, then it gives an alarm. We've also seen scenarios where we have chambers of chemical reactions and we are monitoring temperature and pressure. Those are combinational logic circuits. But in this case, we are now going to look at some more perhaps more difficult ones, I should say, or more significant ones, bigger ones. And we are looking at a number of methods that we can do this. Always the basic method is obviously using Boolean algebra. Now, we say that combinational logic circuits have no memory. In other words, if you have your circuit like this and you have your output here, X, and maybe two inputs, A and B, there's somebody making noise for us in the jury. If you have your combinational logic circuit like this, your output X is that, and you have two inputs A, B, you can have 3, 4, doesn't matter. The idea of the fact that combinational logic circuits have no memory is that X, at any moment, X depends on the inputs AB. Okay, so whatever is at AB determines what is at X. There is no memory in here that influences the output. You might find, for instance, that in some scenarios, and we are going to be looking at some scenarios in the next chapter where you might have this circuit was storing some information before that you can combine with these inputs to make an output. But in the context of combination logic circuits, we assume that the circuit has no memory, meaning that the instantaneous inputs determine that instantaneous output. What I mean is, in any instant, the output depends only on the inputs. Now, we use two techniques. We use Boolean algebra and we use mapping. There's a mapping technique that is really nice and wonderful, and I love it. And I'm going to do my best to teach it in a way that everybody can get it. For it, you don't do algebra, and it always gives you the simplest form of the circuit. So it is wonderful. The objective for combinational logic circuits is really to simplify the circuits and use fewer gates. So you can create a scenario and create some Boolean expression, but the objective is that you must reduce that Boolean expression using Boolean algebra or mapping to its simplest form, and then you design, that is your output design. What this means is that I can have a circuit that has 7 gates, but I can also have a circuit that I can reduce that to a circuit with 3 gates, and they will do exactly the same thing. So then in design, the fewer the gates, obviously the better, because it's a simpler circuit. It will consume less power. It will take less space on the IC, and so on. We have 2 approaches. We are going to use one of them. So when we are simplifying logic circuits, we can express our we can express our Boolean expression, or we can put our Boolean expression in what we call a sum of products form, meaning that we have a product, we sum it with another product, we sum it with another product, and so on and so forth. You should always express your circuits or your Boolean expressions in this form. However, we don't allow, so this product could be AB. Okay, now if I have A, B, this is allowed. If I have A, B, you know, with a bar on both of them, this is not a sum. That expression shouldn't appear in a sum of products form. Instead, we should apply De Morgan's so that we can have A or B. Okay, that now this expression would be allowed. We also have a product of sums. Okay, so let us look at a sum of products. This is ABC, that is a product, and this is A inverse, B, C inverse. This is also a product, and then we sum them. But really, this is sum or we are expressing our expression, we are putting our expressions in products form, and we are ORing those products. If you look here, we also inverse, C inverse, D inverse, and then D. Again, this is a sum of products, what we call SOP. This is A inverse B, that's C. That is also a sum of products. Okay, so all these expressions are examples of sum of products form that I'm talking about. to compare, you have a product of sums. This means you have sum, you multiply it with another sum, you multiply it with another sum, and so on. And you can see here, this is the sum, and it with another sum. Sum you and it with case you have f, but f is essentially equal to f or 0. So f or 0 is f or 0 or 0, you know, so on. So it doesn't mean that just because you have one variable that it is not a sum or like an or it's not an and. It can be an and. So f can also be f and 1, okay, and so on. This is also, again, what we need to remember is that I've also put it here that only individual inversions are allowed in both cases. What I mean is that you shouldn't have something like, so if I have something like in this case, if I have something like ABC or ABC, this is not a sum of product form, not at all. But it can be ABC or A inverse or B inverse or C inverse. Now, this is a sum of products. This is a product, that's a product, that's a product. Never mind that it is just one value. It can be A and 1, that can be B and 1, and that can be C and 1. So they can be products, really. Now, if you look at this, this is AB or CD or E. So this is a product or a product or a product, and that's a sum of product form. This is AB and C or D. This is not a sum of product, neither is it a product of sums, because this is not a sum, the first term. So this can be re-expressed as ABC or ABD. And now we have a sum of products. This is a product of sums. So you have a sum there, and you have a sum, and these are ANDed. And so you have a product of sums. This is the second form. We are not going to use the second form. We are always going to use the first form. So if you have an expression like this, you can multiply it out using the theorems that we saw. And finally, you have MN or PQ. Again, we know that this is neither a sum of product or products or a product of sums. So you need to do something about this to change it, and really it becomes M or N or PQ. Then you have your sum of products. So this is really just the basic. These are the basic concepts that we are going to be working on. And after this page, we go straight into examples. So if you have any questions, perhaps this is the time to ask. Okay. Now, okay. Let me see, Omodo Davis.
So I was asking this, well, if an expression is given and it's not an individual inversion, should we always transform it into, like use the other concepts we have learned to transform it into an equation where it has individual inversions?
Yes, as a rule of thumb, yes, unless we have some expression where there are some gates that we are going to, you know, if you are using NAND or AND, so it really depends on the expression, but most of the time we want to make them individual inversions. So it would have to be a special case where you choose not to do that. But when we are working with Boolean algebra and we are trying to simplify circuits, always convert it. Vivian? Vivian, did you have a question?
Morning.
Yes, good morning.
Yes, I had a question. My question here in SPF and the expressions can S inside another.
I can't hear you, Vivian. Please, the network is quite poor, the audio. Maybe you can type your question in the chat and I'll answer. There is somebody that whose name I don't know, so I won't even bother with that one. Emmanuel Wamono.
Good morning, sir.
Good morning.
You have talked about soaps and you said we are mainly going to use soaps, but I haven't got it clearly why we are only going to use soaps.
Just a moment. The reason why we use so both of these methods are actually allowed. We can use sum of products form or product of sums form. In this case, at least in the book that we are using, we are designing based on sum of products form, and it's just a choice. It's not that the other with with uniformity. Certainly with the book, we are going to be using the sum of products approach, but you can also design your circuits based on product of sums, and that probably will give you still the same size of circuits, so it will reduce it to the same size. You can check that later on, but in our case we choose to use sum of products form just as a choice, as a preference, not to negate the other approach. Okay, so Matthias, I've answered you. The reason why this is that we have mn, the inversion is over both. This is the only form that is allowed, or individual inversions. And I think somebody had already also tried to explain that to somebody else. Okay. So let's move on. So we have a simple circuit like this one. It is saying simplify and draw the equivalent circuit. We have this nature. So we go through the circuit as we move from this side in this direction. So we have BC, and on the output here, we know that's BC. Now that's A, so that is going to be the inverse of A. And then we have here, we are going to have A inverse or BC, okay, with an inversion on top, because this is the NOR gate. And we have, obviously, here we have B, and then here we have A. Right, you can see the lines from B and that line from A, meaning that my X, because this is an AND gate, my X now becomes AB, okay? And I can even put this one in a bracket, A inverse or BC with an inversion on top. So this is, we've done this before. At least everyone knows how to do this. Now, this is not certainly in a sum of products form. So we want to put it in sum of products form. So we can use the Boolean algebra approach. We are going to look at the mapping approach later, maybe in the next lecture. So so now how do we begin? We just say AB, always start looking at these terms that have the bar. Those terms that have the bar is where you usually start your simplification. So for instance, this one, because we have this, remember we have something like X or Y bar is X. Is our one of the rules. The other one obviously is that X and Y bar is X or Y. Okay, so these are the two De Morgan's theorems. So if we look here, we are going to have A double bar and BC with a bar on both of. And for simplification, looking at this, so this really becomes now AB and A. And if we look at this one, now it becomes B or C, each one with a bar. Okay, this double inversion here just goes off because, and then we have now A, B, A, and B inverse or C inverse. We know that A and A is equal to A, so that if you have 1 and 1, you have 1. If it is 0 and 0, you have 0. So that means this of this and that will retain AB, B inverse or C inverse, A, B, B inverse, or A, B, C inverse. Obviously, I'm doing this in so many steps. With experience, you won't need to do all this stuff. You can quickly kick out things. So now if we look at this term, we have a B and a B inverse, and we know that's a 0. Because you have a 1 and a 0 gives you a 0. But if B was a 0, B inverse is a 1, you still get a 0. So then we say that our X is equal to AB, C inverse. Okay. This term and that term are essentially the same. If we want to draw our equivalent circuit, because it is simplified, we've done equivalent circuit. You can see that's an AND gate with 3 terms. Okay, so we have A, B, and C is inverted, right? And on the output we have X. So do we first convert all the options or we immediately answer? Vivian, so what we do, I think this now slide answers your question. Depending on the equation you're given, you need to first express it into, you should be looking to express it. All the stuff that we is a product, and that's a product, and we are ORing them or summing them in quotes. Value, this term actually goes to 0, meaning that we remained with one term, with one product, so that there's no ambiguity there. So you can see here, you can see actually what we have done is exactly what we have here. Okay, you start with a huge expression and you end up with a simplified expression by following the rules that we have studied, which are the theorems. We look at we basically use those Boolean theorems to reduce this thing, just like you would in algebraic mathematics, in just normal mathematics. So let us look at this one. Again, this one is very easy. It looks big, but it's very easy. By the way, before we leave this one, this circuit was using 1, 2, 3, 4. Now the equivalent circuit uses 1 and 2, just 2 gates. So clearly you have simplified this. Usually simplification is measured in the reduced number of gates. And we know why we want to simplify. I've already mentioned that. Now, if we look here, this one looks like a huge thing, but it's really not. Let us go through this. 1, 2, 3, 4, 5, 6, 7. These are 7 gates. This is A inverse. Okay, so this will be A inverse, that will be B inverse, meaning that here we have, okay, here we are going to have, because this is an AND gate, we have A inverse and B inverse, but with a bar on top. No, it's actually C, sorry. C on top, which is that term. Now this A also comes and is fed into this AND gate. If we look here, we have a B inverse being put into this AND gate. So that means that the output, we are going to have A, we are going to have B inverse, and then this term. which is A and C inverse, the whole thing inversed again. From down here, we have ABC. You can see that line, and that line, okay? Meaning that on the output, we are going to have ABC ANDed with that. Or it is ORed with that one. So now the question is simplify and draw the equivalent circuit. Francis Camille, you are making noise for us. Guys, please keep yourselves muted. So isn't there any other way to represent that other than using a single gate and gate on that simplified term? Of course, there is another way, but here why we can use just one gate is because for the AND gate, if you don't, I already told you that if you don't have 3 input AND gate, you can use a couple of 2 input AND gates and it would work out. But the problem is you are increasing the number of gates, so it's okay. We can look at this as simple. There are always other ways to express these things, but they may be less efficient. Patrick, now why are you? I removed Patrick from the class. I mean, why is he talking when we are in the class? Guys, these are the things I'm talking about. Okay. So I'm seeing Semakula Musa. We have been doing that as normal simplification of Boolean algebra. Is there any difference or just giving the approach a name? Exactly, Musa. We are just giving the approach a name. I said that this chapter is not going to let us do any new things. We are just going to do more complicated things, perhaps. We are going to also look at a couple of other gates in this chapter that we have not looked at before, but essentially we have already been doing this, and it is, yeah, if you like, we are giving it a new approach. Anyway, let's try to simplify this. We have Z is equal to A, B, C. That's already a product, so we are not going to touch that, hopefully. Or we are looking at AB inverse and AC. This is inverse and inverse with another inverse. Let us start here. This is going to be A inverse inverse or C inverse inverse, which will end up being A or C, meaning that we have A or C and AB inverse. Okay, remember from up here, then O ABC, meaning that our Z now becomes ABC. If we multiply through, we are going to have A, B inverse, or that is becoming AB inverse C, AB inverse C. And so this goes away. We have ABC or AB inverse or AB inverse C. So now we continue our simplification by looking at this term. This term, we can see that there is a common term, AB inverse, and here we would stay with 1 or C. We know that 1 or C is 1 because whatever C is, as long as we are ORing and we have a 1, the output would be a 1. Then we have ABC or AB inverse. All right. So how do we proceed here? Do you see any other way that we can simplify this?
Yes, sir, I can see as if there is another way.
Yeah.
We can have A out.
A
out
into B inverse.
B bar plus BC.
BC. Good.
Yes.
Now we know that X inverse or XY, please mute yourself, is equal to X inverse or Y. I think you remember that theorem. Those are the 2 theorems before the De Morgans that I talked about. You really need to remember those theorems. Then we end up with A. In this case, our X is like B, so we have B inverse or C. Now, here you can actually stop here, although this is a product of sums, it can also, you can also call it AB inverse or AC. I mean, these two can be your final output. Let us try and draw the circuits. You're going to have A, then B inverted, and then you're going to have C, all right? You can put these in an OR gate, and then you AND them, okay? A, B, C, X or Z. Or you can have that you AND these, right? Then you can have AC. This is A, B, and then AC. You have another AND, all right? And then you OR these together. So as you can see, this is Z. As you can see, here we have 4 gates. Here we have 3 gates. So this is a simpler form of, instead of this, we have a simpler form here. Usually you go with the simpler form. So we want to go with this. Let me see. 1, 2, 3. I think that's what we have, B and C, and then we AND it with A. Okay. So we have seen that this equation is equivalent to that equation, and you can see that this huge circuit that we were scared of can actually reduce significantly to something with 3 gates. Let me look at some. Yes, thank you guys. So at least I can see that you know what we are doing. I keep simplifying at the buried gates before the next gate. Chris, I don't quite get your question, but just keep simplifying things as long as, obviously, if you want, maybe now I get what you are saying, that can you simplify at this stage so that you have A or C? Yeah, you are more than right to do that, or you are more than free to do that, because it's the same thing really, because when we come to this expression, still we go through the same procedure. So you can do that, but just make sure that you do not make a mistake, okay? A bubble means inversion. Doctor, can I use instead of the inverter? I don't actually know what you mean, Musa, but if you look at the inverter already has a bubble. So this already means an inversion. So if you want, maybe what you mean is, if you say, you put your bubble there, and that, meaning BC, and then you have your AND gate here, A. Yeah, so this is fine. Generally, that is fine. I really don't, I mean, it's not that I want to discourage it, but you can use it. But I think, sometimes when we are grading you, we are moving very fast. And so if anything looks a bit different, it can be, but I think you would be more than right to actually do that. Okay, so let's continue. I'm going to give you something to do for me. Got a few other things that help us to learn a few more concepts in terms of simplification. So we have this expression. Now, the question is, where do we begin? There are probably different ways you can simplify this. Let us first of all look at these two terms. Okay, so we have A, B inverse, C inverse, this is Z, or AB inverse C, or ABC. Let us look at these last two terms. AC is common, meaning we have B inverse or B. B inverse or B is 1, as we already know. So we end up with AB inverse C inverse or AC. Now let us remove A, which is A, inverse B. Now we know that X or X inverse Y is equal to X or Y. Yeah, I think that's the one. So we end up with A. Now X is our C, or, but that's a B inverse actually. C or B inverse. And I don't think you can simplify it. Oh, but now we or AB inverse, or our first term, which was AB inverse, C inverse. So if we remove, now if we look at this term, see the problem is these things can be confused. Depending on how you approach it, you can easily get confused. So we have A, B inverse, or B inverse, C inverse, which becomes A in yes, or our AC up here, and that is Z, which becomes AC or AB inverse or AC inverse. Now, as you can see, we continue. It's a long journey. Now we can say that Z is equal to, if we look at the first term and the third term, we have A. That is, in fact, we can say A and pull out C or B inverse or C inverse. Now C inverse, C or C inverse is 1, meaning that we have A into B inverse or 1. Which gives us A. That doesn't sound like it is true. I think we probably made a mistake.
Excuse me, sir. We actually made a mistake. Our final answer was supposed to be A into C plus B inverse. We had already added the first term.
So where should we go back to? Here.
We should just stop there.
Hey, why did you let me continue? Yes, we had already added the first term, which is yes. Why did you let me continue? Anyway, you have got you have seen how, yeah, but you're right that our answer, because obviously we got the AC from up here and then we added that, and we should have stopped here. So thank you for letting me continue and do rubbish. But then we can see that Z becomes A, B inverse, or C. There's something I wanted to show you. Another method. I don't know if it will work. Okay, with Boolean algebra, sometimes you can go you can go in circles. Let me see. So if I have this and that, and if I have this and that, I'm trying to see if I add a B inverse C, and then here. Okay, so I can say, let's see if this works. Trace, I'll be with you in a moment. Let's say that I have a B inverse, C inverse, or AB inverse C, or I can add this same term again, AB inverse C, and then I add ABC. The reason why I've added this term twice is because I want to simplify my my expressions, but like the Boolean algebra, but actually it doesn't make a difference. It's like A or A is A. So adding this twice does not make our expression wrong necessarily. But what we have now is we can consider these two and these two. And if we do that, we are going to have AB inverse, C inverse or C, or in this case, it will be AC, B inverse, or B. So then we end up with AB inverse or AC. You see, very quickly you get your answer, which is A, B inverse, or C. So sometimes you look usually with expressions of these terms where the terms are similar, but some are inverted and some are not. You can look at a way of you can look at one of those terms and add it twice or thrice or even 5 times, depending on how long the equation is, so that you can actually simplify equations 2 at a time. Let me see. So Tracy.
Excuse me, sir. I think you are moving on and yet we are not hearing. I think you're muted.
Yeah, I was actually muted. Thank you. Yeah, so I was saying that here we have seen 2 approaches. This is easy because this is how we usually do it. But on this side, we have seen a new method where we can introduce the same term twice. And I was saying that you can introduce it as many times as possible, but make sure you introduce the same term, because this would be we know out of the theorems that if you have A or A, it remains as A. So it's not like you have changed the meaning. But it is a new technique that you guys can use to actually quickly arrive at your final answers. You find an appropriate term, and in this case, we've added this term, but I had to first look at, if I add this term and I attach this one here and I attach this one here, do I actually simplify? Because if you, for instance, added, instead of ORing this, you ORed ABC again, it may not give you the simplification, the quick simplification that you're looking for. You'll still reach the answer, but not in see which one you can or out of the 3 terms that you have. Okay, things are getting interesting. I don't know if you want to do this one. Okay, but I don't want to go through with it. You can work on it. It's a bit large. Okay, but you try it on your own. I will also try it on my own.
Excuse me, sir. Guys are saying they can't hear, and yet I I remember you've said that we try and do the numbers ourselves, but these guys are saying they are not hearing.
It's because I'm not talking. Since you are doing it on your own, I don't really have. But I'm also just trying to do it. So you guys do it. I'm just also trying to do it. We will see. So I don't expect anyone to be doing this. To sort of be just following. You should be working on the number. Okay, so I wasn't talking. That's why you couldn't hear. Yes, thank you, Charles. I had actually made a mistake on the D inverse. I had forgotten the inverse on D here, and that's what was giving me problems. So if you make a small mistake, you're not going to get this. Also, there is no guarantee that you're going to get this. So sometimes I encourage students to actually use the Kanoff mapping approach to simplify these things, because for it you cannot make a mistake. It's just impossible to make a mistake unless you don't understand the mapping. Students are not always comfortable with the maps, as unfortunately. So okay, but use a method that gives you the simplest answer. Sometimes, of course, I will say use this method, okay, so that you don't always shy away from whichever you don't like. But if you have time and you want to, you can always use the Kanoff map to check your method to see if it is correct, etc. However, you can see that it is a bit involved to actually reach the final correct answer. So let us continue. Very good, guys, those who got it. Okay, so we have this. So this is I think this is the method that we have just used. Now in the book, there's this. In fact, you see we have got B inverse C or A inverse, D inverse, B or C, right? This is the method, our method gave us this one. But in fact, in the book, it shows you that the actual simplest form is in fact this. But the point is, how do you even get to that? How can you move from this point to that point? There is no clear way of moving from that point to that point. And if you use the Kanoff map, the mapping approach, it would take you straight to this simplest form. So that is why it can be a better method sometimes. And so it shows you that the Boolean algebra might not always give you the simplest form, but more often than not, you're going to get the simplest form. Okay, so this is for you. You do this one and then let's see. And please text your answer. All right. The two, Ivan and Musa, this is correct. With the rest. So we can still have our A or B. And then we start with this D, we move it in here. So we have, depending on how you want to expand this, you should still reach the same answer. AD inverse or BD inverse or DD inverse. We know this one will go to 0. We can now multiply through this. We have A inverse AD or A inverse BD inverse AD inverse. Or now we start with B. We'll have B AD inverse and then B BD inverse. This one will also go to 0. So we have we are left with A inverse B D inverse or AB D inverse or BD, okay, inverse, because BB is B. And so if we say BD inverse, it is common. We are going to be left with A inverse or A or 1. The moment we have a 1, makes this whole thing 1, and we end up with BD inverse. Okay, so if you have the same answer, it's okay, guys. If you have the same answer, if you see that somebody has already posted your answer, then it's fine. Okay, thank you. So this is an interesting circuit. In fact, we are going to see later on that it can. We have gates that that do this type of circuit. So we have A inverse, and here we are going to have B inverse, meaning that here we have A inverse or B, and here we have B inverse. We have A or B inverse, meaning that our Z is actually A inverse or B and A or B inverse. Now this is a product of sums. We need to make it a sum of products. So we can say A inverse A or A inverse B inverse or AB or B inverse. That goes, we have A inverse B inverse or AB. If we want to design this, we are going to have A and B, okay? These ones will go through an AND gate, and then we are going to have AB, right? Also going through another AND gate, and these two go through an OR gate, and we have our Z. Here we have 1, 2, 3, 4, 5 gates. And here we have 1, 2, 3, 4, 5 gates. So in fact, much as we have done some gymnastics, but we haven't done any simplification. So there are also certain cases where you may not actually do any simplification, as in this case, much as the circuit has changed, but the size of the circuit is still essentially the same. We have two inverters, 2 OR gates, and 1 AND gate. On this side, we have 2 inverters, 2 AND gates, and 1 OR gate, essentially the same thing. Okay, you can see no simplification. And it is not possible to simplify this further. In fact, we are going to see that this expression is a gate. There is also this. I give you an expression like this, and you simply cannot simplify it. All right. So, I mean, there is no way you can simplify it. At most, you might express it in a different form. That's really it. Here, there is even no common factor in any two. So it is impossible. So I want to give you a poll. You know, you simplify this one. In approximately 1 minute, I'm going to put a poll up, and then we can put our answers quickly. So you simplify that expression. I don't want your answer. I said that I'm going to launch a poll and you give me your answers. All right. So please, please let this take just 1 minute so that we can. I'm going to end this in about 1 minute. It's almost 2 minutes, and I'm going to be ending this poll in 8, 7, 6, 5 seconds. 2, 1. Okay. So if you look at these two terms, you are going to, or you can actually just, you can see T inverse is common. So you have T inverse, which is RS or R inverse S or 1. The moment you have a 1 here, it negates all these, and your answer is simply T inverse in just one step. Right. So I'm still, by the way, unable to understand how some people are not getting the poll. How is it possible that some people are not get the poll? Okay. Anyway, I'm sure if you've answered, your answers are there. So let us move on. Let us look at how we can design logic circuits. So usually when we are designing logic circuits, and this is where we use the knowledge that we have been learning, is we know what we want, but we want to design the circuit to give us that we want. Kaketo Francis, you guys, I don't know. It's just funny. So we know what we want, and we want to design a circuit that can give us what we want. So let us look at an example. This is an example. We know the truth table is like this. In other words, here we want a high when A is 0 and B is 1. And only in this case do we want a high. All other cases, we want a low. So we can draw a truth table, and from the truth table, we can design our circuit. In this case, we can say that X, our output, is clearly A inverse B, okay? Is clearly A inverse B. So what you do is, once you have your truth table, you look for the scenarios where you have a 1, and you make that form. In fact, let me just draw some random circuit where we can start. So let us say that we have a circuit. We want a circuit that produces a high when A is equal to B is equal to 0, or A is equal to 1. A is equal to B is equal to 1. When, okay? So we can say that, okay, we have A, B, and our output is X. We know it's 0, 0, 0, 1, 1, 0, 1, 1. We are saying that when A is equal to B is equal to 0, we have a 1. And when A is equal to B is equal to 1, we have a 1, meaning that these other cases, we have zeros. So what we are interested in are these terms which give us a 1. And this term us B, and this term is clearly A, B, because they are both in their active high states. And then we can express our Boolean expression as follows. We say X is equal to A inverse, B inverse, or A, B. We ignore these terms which give us a 0. And then from here, you can now start doing your Boolean simplification like we have already seen. So in a logic circuit, I tell you what I want, and you design a circuit that gives it back to me. Okay. Let us look at this one. Actually, this one now is the opposite of what we have seen. We are saying that we need a high when A is not equal to B. So when A is not equal, here A is equal to B, and here A is equal to B. When A is not equal to B, it is this term. So you have a 1. A is 1, B is 0. Again, they are not equal. You have a 1. And then you can see that this term, X is clearly A inverse B. And in this term, A, B inverse, and your output becomes, you sum the two products, A, B inverse. You end up with, that's your term, and you can draw the circuit. It will be made of 5 gates and so on. Another thing is this one that we have just done. I think we had already drawn this one anyway. 2 inverters here and here, then 2 AND gates here, and then an OR gate. Again, we are going to see in a moment that we have gates that, not in a moment, in the next few lectures, that we have gates that give us this expression and gates that give us this expression. This is an expression. The gate gives you an expression, an output that is high when the two values are not equal. Whereas here, the gate gives you an expression that is high when the two outputs. Right. they are like a combination of these simpler gates, but we are going to study more when we get there. So so let us look at more complicated scenarios. We have a case here where we want to generate a high. We have a high when two inputs A and B are different, right? That's when we want to generate a high. And yet we have three inputs here, so it really doesn't matter. We only focus on A, B, because those are the ones that determine the output. C does not determine the output. But we have, you can draw your circuit of three inputs. I don't even know why this one has. They would have mentioned that consider a 3-input logic circuit that generates a high when the two inputs A and B are different. So we look at this. Here they are equal, here they are equal, here they are different. So we put a 1. We are not even concerned about C. We are looking at this. Here they are different, we get a 1. Here they are different. When the two inputs A and B are different, well, here they are different, and here they are different. Did I write it correctly? Let me just check the book in one moment. I don't know. I think this, yeah, I think this statement shouldn't be here. It comes from this last I keep duplicating this, so I clearly forgot it. So this is not a thing. Let us just forget about it. This just expresses what we were talking about earlier. Imagine you have a 3-input circuit whose truth table is as follows, yeah?
So I've not understood what you are doing.
Buhari, I've removed you from the lecture. So you have a scenario where this term gives you 1, that gives you 1, and this gives you 1. I don't know what it is they are doing here, but usually I will have given you a clear in 0. But generally, if you have a truth table like this and you have 3 terms that are 0, you actually write them in product form. So you can see that this is A inverse B and C inverse, because A is a 0, B is a 1, C is a 0. Then this is A inverse BC, because B and C are 1, and then that's ABC. And then your expression becomes the terms which are. Let us look briefly through the procedure. I'm going to explain. Let me explain the procedure. So when we are doing our design, just I'll be with you in a moment. When we are doing, all right, I'll tell you, for instance, that design a circuit. You have a 3-input circuit that produces a high when it could be, let me say, I give you a 3-input circuit. Any 2 or more inputs similar. Okay, something like that. So let's even do it here. A, B, C, and X 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Actually, but when, let me change my question. When the three inputs are similar. So we have a 3 input circuit that produces a high when the 3 inputs are similar. The 3 inputs are similar when they are all 0, meaning then I'll get a high here, or when they are 1, meaning I get a high. All other cases, they are not all similar. So I just put 0. And then I was saying that here, I express the ones, when the output is 1, I express those. Okay, you can see write the AND term for each case where the output is 1. So I can have A inverse, B inverse, C inverse, and here it will be A, B, C. And then in the third, write the sum of products. Okay, so then my output X is equal to A inverse, B inverse, C inverse, or A, B, C. That is the third. Fourth, simplify the output expression if possible. We know how to simplify. Unfortunately, here we cannot simplify. And then you can implement the circuit using that final simplified equation. So you can draw your circuit. And so what I was saying here is that you could have a scenario where your truth table looks like this. Only concentrate on the terms that have ones, write them in their product form using their states, and then do a sum of products and try to simplify if it is possible. After simplification, you can draw. Guys, I'm going to remove you every time you make noise for us. So let us look at some examples. Okay. This is a good example. So I think it was Tracy who wasn't understanding. This is your chance to understand. Sometimes it was Vivian. Sometimes I try to give you some ideas first, but in general, it is always better to learn from examples. So here we have a logic circuit that has 3 inputs, A, B, C, and whose output will be high only when a majority of the inputs are high. So every time we have a majority of inputs are high, then the output will be high. This is your interpretation. The first stage is to interpret the problem. The problem is that you have a 3 input circuit. The output is high only when a majority of the inputs are high. Now, what is a majority? If you have 3 inputs, a majority is 2. So that means that every time you have 2 inputs, so more high, and more really is 3, either 2 inputs high or 3 inputs high, then your output is high. So let us draw our truth table. A, B, C, and X. So we are going to have what's happening. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right. So here we want a majority of inputs to be high for us to have a Y. Here a majority of inputs are not high, so we have a 0. Here we are having a 0. Here it's only 1 which is high, we have a 0. Now here we have 2 inputs are high, so that's a majority, so we have a 1. Now here we have only 1 input, so that's a 0. Here we have 2 inputs high, so we get a 1. 2 inputs high, we get a 1. And 3 inputs high, we get a 1. Because 3 inputs high is a majority, of course, it's also in the majority. So that was our step 1. Now this is our step 2, which is doing the truth table and then writing the AND product. So we only look at these terms which are high, and clearly this is written as A inverse BC. This is going to be A, B inverse C. This will be written as A, B, C inverse, and that will be A, B, C. So our second stage, really, we write our sum of products. No, that is now our third stage. You don't have to remember these stages, but I'm just saying them so that at least we know we are following the right procedure. Now I'm going to write my sum of products, which is X is equal to A inverse BC, or A B inverse C, or A B C inverse, or A B C. Now my fourth stage should be simplification. Now, really what we have done here is that we have changed a statement in words into a Boolean algebraic expression. So then now we can just do our simplification from here. If we look at the first two terms, let's try to simplify. I don't know here the best approach, but if we look at this, for instance, we are going to have AB. How do we simplify this one? What is common here? What is common here is C, but if we do C, then we don't really simplify what is inside because it will be A inverse B and AB inverse. So that is not going to take us far. What if we consider this one and then these two together? What does it give us? Again, it is not going to give us much. Okay, but if I consider this and that, you can see that trying to simplify using this procedure is not always the simplest. But what we can do is so our simplification can take this form. Because we see that only one term has a bar, we can add this to every term. So we can have A inverse BC or ABC. Then we can have the second term, which is AB inverse C or ABC. Then we can have the third term, which is ABC inverse or ABC. Okay, we haven't changed the meaning because ABC, ABC, ABC still gives you ABC. Now it means here we are going to have BC, A inverse or B or A. Here we are going to have AC, B inverse or B. And then the last two terms we are going to have AB into C inverse or C, which becomes AB or BC or AC. And then the fifth stage is to draw the circuit. Usually in an equation, I might tell you to draw or not. But if you are drawing, now you know how to draw this one. These are 3 AND gates and 1 OR gate, 1 3-input OR gate. Okay. So that is how we design logic circuits. I want us to look at a couple of, in fact, this is what we have just done. Let me give you another example. A 3-input logic circuit that returns a high when the decimal of the input combination CBA is greater than 4 to the base 10, right? So we are saying that we have our input combination CBA, and when this combination is greater than 4 to the base 10 in decimal, then we should have a high. So we can say CBA, clearly here you've been told what is the most significant bit by giving you this term, X. You have 000, 001, 010, 011 100 101 110 111. Now the decimal equivalent, you don't have to put it in the truth table. Here the decimal is 0, 1, 2, 3, 4, 5, 6, 7. So it means that we want CBA to be greater than, not greater or equal, but greater than 4. 4 base 10 is that one. So it means 0, 0, 0, 0, 0. We are going to have a 1 and a 1 and a 1 here only. So I hope you can understand how I've got this truth table. And then this we can write it in in its product form, which is CB inverse A. This one CBA, and this one CB A inverse, and this one is CBA. So then we can write our sum of products as CBA or CBA inverse or CBA. And this really becomes, I can call this CB inverse A or CBA plus CBA inverse or CBA. And then I look at two terms at a time. This is going to be CA, B or B inverse, okay, B inverse there, or CB of A inverse or A. And then we have CA or CB, or essentially C into A or B. So instead of having this term, now we have this term, our circuit as A touch the gate, because if they don't touch the gate, then you might have a problem. And that's C, and then we can AND, meaning that now if we have this, is that this circuit is actually going to implement this term. This circuit will always return a high when the combination CBA is greater than, as simple as that. I'm getting A, C inverse or B. Why? I don't know how you have done it, Jess, but you could also, we might be wrong and you are right, but I think you should look at your work again. Excuse me. So let us look at a few more examples. Chihembo Susan, it is not always easy to know which one to add twice. Every time, if all my terms, only one one input has a bar. So like in this case, it's one input. In this case, it's one input. Then I can add this term again, the one which has no, because you're trying to eliminate, to make sure that if you have a bar here, you add it with something that does not have a bar. But there is no rule of thumb to follow really. It's all about analysis. So, when you are doing mathematics, you're looking what is common and how can I manipulate it. It's all really algebraic manipulation, and I'm not very sure anyone can teach you that. You just have to look at the terms you have and try to make sense of them. Let us see if something like that might work. Let's see, another term is okay. So what if we said CB inverse A or CB A inverse or CBA inverse or CBA? So in this case, I've added this term twice. Then I have here, I'm going to have, do I have anything common? Already I'm in trouble because this only C, it doesn't give me any commonality. So that is not going to work. So you can see that usually there is only one term that will give you what you want, and that could be a start. Okay. designing logic circuits. I think we did this one. Now let us look, let us do, this one is going to be quite strange because this is an application of logic circuits that we do in third year, sorry, in applied. But let us read through this. Refer to figure 4.8a. Let me see if I can find that figure for you. All right. All right, so this is the figure. Right, so I'm sure you can see that. So this figure is an analog to digital converter. You know, when we have an analog to digital converter, it means that on this side we have analog, and on that side we have digital, and digital is in bits. In this case, we can see that it is A, B, C, D. So it is saying that the ADC is monitoring the DC voltage of a 12V storage battery on an orbiting ship. Okay, so here we have voltage. It is analog voltage, and it is a 12V DC thing, but it can change. And you can see it's here, right? It can change. So you have ground, but the voltage is going into an ADC. This is an ADC. Now, the converter's output is a 4-bit binary number, ABCD, corresponding to the battery voltage in steps of 1, meaning that if you have 0 volt, you might be having 0, 0, 0, 0 on this side. If you have 1 volt, that's why they are saying in steps of 1. So the voltage changes in steps of 1. Maybe 1V might be equivalent to 0001, 2V, sorry, and so on and so forth. So that is how ADC is working, but we don't really care for that side. We are only interested in the digital. If we were doing the third year course, we would be interested in the whole thing, but right now we are only interested in the digital side. A is the MSB, so A is the most significant bit. The converter's binary outputs are fed to a logic circuit that should produce a high output as long as the binary value is greater than 6. Decimal 6. 6 in decimal is equal to 0110, because that will be 2 to the power 2 and 2 to the power 1, which is 6. So the output will be high if the binary value, which is A, B, C, D, is greater than that. So the battery voltage, meaning the battery voltage is greater than 6 volts. Design this circuit. Now, what could be the purpose of this circuit? This circuit could be simple. You could be saying that actually, I want this to go into, this circuit to go into like a bulb, okay? That's a bulb, so that if my voltage goes beyond 6 volts, I have light. If it's below, I don't have light. So that could be telling me maybe 6 volts is bad, or anything beyond 6 volts is bad. I don't know. But it could also be feeding another circuit and doing some other purpose in there. But it could be just as simple as at the output there, I can put a bulb. So the first thing is we have interpreted this. We know that we have 4 inputs, A, B, C, D. We are going to draw a truth table. And the truth table, X is high when A, B, C, D is greater than 0110, which is equivalent to 6 in the base of 10 in the decimal. So you can see we have our circuit here, and everything will be 0 up to 6 decimal 6, which is 0110. After that, everything is 1. And so the next stage is to get those terms that are 1 and write their product form. So that's A, B, C, D, A, B, C, and D inverse, and so on and so on. If you write this wrongly, you're in trouble, but at least you've already been told that A is the MSB. And then after you sum up this stuff and you simplify it, it looks like when you simplify it, you get A or B, C, D. I don't want to tell you, but such a thing is going to take you a whole page to simplify. But you should try it later. I think even in the book, the whole working is in there. We are not going to do it here. But you can see that from something that could have been very big with so many inverters and so many OR gates and so many AND gates, we have ended up using just 2 gates, 1, 3, and 1, 4, right? So this is a logic circuit, okay? And you have to design it, and you have been given all the information you need. And the information is that that logic circuit should detect when the voltage at the input, you know, when when this voltage is greater than 6V, when VB is greater than 6 volts, it means that the output of this ADC will be greater than 0.110 to the base of 2, and that should return a high. Otherwise, the other situation where it is lower than that it is equivalent to that or lower, it should return a low. So that is somebody has given you the logic they need in their circuit, and your job is to design for them that circuit. And that circuit, as we can see, can be so simple, just made up of 2 gates. It means that for each of these combinations, you're going to have an output. Let me, for instance, look at this. ABCD is equal to 1, 0, 1, 0. You have a 1 and a 0, a 1 and a 0. Actually, here it's already showing you that if A is a 1, it doesn't matter what that is, whether that's a 0 or 1, your O will be out. What about a case like here where A is a 0? Because as long as A is a 1, it's already. So it means, let's remove this. You have a 0, 1, 1, 1. If it is a 0 here, then this 1, 1, 1 will produce a 1 here. So you still have 1 or 0 here, giving you a 1. So the 6 is what a decimal value is obviously in base 10. So that's why we have 6 to the base of 10 here. 6 of base in base 10 is analog, really. And to answer Semaganda Raymond, Chinobe, you can go and read your gray code. It's in the book. Let me start with you. Semaganda Raymond, the importance of the MSB in this case. If you don't know the MSB, so let's say we have like A, B, C, D is given to you as 0, 1, 1, 1. If you don't know that A is the MSB, because these are weights. If an MSB has a weight that is greater than any other number. Now, if you wrote this one as DCBA, because you don't know which one is the MSB, then you have 1, 1, 1, 0. Now, these two things are not the same. So you'll already be in trouble. It's important to always know what the MSB is. And if you've not been told that the inputs are written as A, B, C, D, then it is implied that A is the MSB. If it's been written as DCBA, it is inferred that D is the MSB. Otherwise, if you are doing your own thing, you need to remember what letter is your MSB. Let us look at another example. This is figure 4.9a, I think. We have figure 4.9a, but let's first read the whole circuit. It is a simple copy machine. So you know these photocopiers. In a simple copy machine, a stop signal S, so it can be high or low. You have a stop signal. If it's high, maybe it might say stop. If it is low, it says continue. Okay. It is a stop. It is generated to stop the machine operation and energize an indicator, meaning that this signal will not only stop the machine, but it will also energize to show that there is a problem, so that if you are the photocopying person, you know, okay, there is an issue there. It energizes an indicator light whenever either of the following conditions exist. The first condition, there is no paper, okay? So we can say the first condition is P, okay? If there is paper, say P. If not, that case could be P inverse. You know how these photocopiers work, don't you? They work in such a way that if there is paper, it will continue working. So you could say that no paper, which is P inverse, will give us a problem, or will give us a stop sign. The second one is that you have two micro switches in the paper path that are activated, including a jam, indicating a jam in the paper. So we can say number two, we can have two inputs Q and R. Okay, these are two switches in the paper path that are activated, indicating a jam in the paper path. Both of them activated, which is, so that might mean that if there is paper jam, then QR is equal to 1. It is ANDed because it's both of them. Else, both Q and R is equal to 0, meaning that if either one of them is activated, it's still not enough. Or both of them are off, that's okay. But if there is a paper jam, both of them must be activated. Now, the presence of paper in the feeder tray is indicated by a high at logic signal P. Okay, so we have already seen that. If paper exists, we have P. If there is no paper, we have Q. And then each of the micro switches produces a logic signal Q and R that goes high whenever paper is passing over the switch to activate it. Okay, so it looks like when there is a jam, paper will pass over the switches and activate them. And by activating them, it gives them a high. So we want to design a logic circuit to produce a high at the output signal S for the stated conditions. And then we can implement that using a quad 2-input NAND chip. I think you remember when we were looking at those chips. So what we start with is our inputs. We can say P, Q, and R. And this is our output S. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right. So our input, when P is low, right? No paper. No paper means P is equal to 0, because you have been told here that the presence of paper in the feeder tray is indicated by a high at the logic signal P. So that means no paper means P equals 0. And when there is no paper, S is 1, right? We have already been told that S will be high, will be energized, you know, when there is no paper in the tray. So every time P is a 0, we should make S 1. It doesn't matter what Q and R are. So we have a 1, 1, 1, 1. Now we are done with that because these other 4 terms, P is equal to 1. So that's okay. It means there is paper. Now for the second case, we are saying that each of the micro switches produces a logic signal Q and R that goes high whenever the paper is passing over the switch to activate it. But from here, we know that the 2 micro switches should be activated simultaneously to indicate a paper jam. So that means that we are looking for a scenario where both Q and R are activated. And we have that and that, but it's already 1, so that's okay. The next time both of them are activated is here and here. So that means much as there is paper in this scenario, the 2 switches have been activated, indicating a paper jam. These other cases are 0. So then we can go now to create our products, which is P inverse, Q inverse, R inverse. Here is P inverse, QR, Q inverse R. Here is P inverse, QR inverse. And here is P inverse QR. And down here we have PQR. As simple as that. So we can now go and try to simplify this equation. Let's see if we can try to simplify that equation. Actually, we can do it here. Just one moment. Okay, let's try to simplify this equation here. Let's look at these two terms. So S is equal to, those two terms will give us P inverse, Q inverse, because R and R inverse will go. And these two terms will give us P inverse and Q, because R will also go here. And then we add our PQR. Now here, what can we remove? Can we look at this? No. We can look at these ones, which is P inverse. Yeah, Q inverse or Q plus PQR. So we are left with P inverse or PQR. And this is the form X inverse or XY. So our S becomes P inverse or Q. This is, yeah, this is the form X inverse or XY, which gives us X inverse or Y. All right. So we can reduce that to this format, and then we can draw our circuit. And I'm going to tell you why this makes sense. This is PQR, and then we have our OR gate. Let me tell you why this makes sense. First of all, we have two scenarios that can make S high. And those two scenarios, any of the two scenarios can make S high. It's not that both must happen. Any of the two can make S high. You can see S is to be generated to stop the machine and energize. It will, the S will be high whenever either of the following conditions exist. So that already the either means an OR gate. The first case is when there is no paper. So when there is no paper, that's P inverse. The second is when the two indicator lights are on, or the two micro switches are activated, showing a paper jam. So it is either there is no paper, which is indicated by P, inverse P, or the two micro switches are activated, indicating a paper jam. In other words, somebody could have come from this statement and could have seen that actually S is equal to P inverse or QR. And we had them because we had P inverse here, and also we had QR there. But we have gone through a number of stages to show you the working. And you can see here, just give me one moment, I'll come and we finish this equation. Let me just have some water. Okay, I'm back. I think we are left with just a few minutes and we stop. So now we have this, but we have been asked to implement using the NAND, NAND gates, because you have only access to that code IC that has the NAND gates. So we know that this is P and Q, QR, and that's P, and we have an OR gate, and that's S. So I just brought these equivalent gates here so that we can actually use. You don't have to cram this. So the first one, the P, is written as that inverter. You can see that's an inverter. So we write P together with NAND gate. The NAND gate has P going into both inputs. And then down here to AND Q and R, we are going to have Q and R. You can see how the AND gate is drawn. And then we pass this output through another NAND gate. Okay. And that should be, so here this is P inverse going to be Q and R. Okay, like that. So this arm will go through another arm. Okay, so we are now drawing this NAND gate, which is that, which is that, and then we can pass those two through another NAND gate. So you can see that the NAND gate has two inputs, but really this is our P inverse, and that is our QR, so that at the output here, we have P inverse or QR. And this is now our output S. And you remember we said that if I have P inverse, it means I have P here. And if I have QR, I don't know what I have here. I think I have QR. It means that these are like inverters, if you notice. It means that here, I'm going to have like QR inverse, technically, which is, you can see that you have B, then B inverse, and then you sum up. So in other words, I can actually remove these two inverters. I can take out that group, and I can also take out that group, and I will remain with an AND gate here, which you have Q and R. You have an AND gate, and you have another NAND gate there, right? So we have already looked at something like this. I really like this kind of thing. So I don't want to say that I'll bring it, but don't be surprised if I bring something like this. And so instead of drawing it like this, we can actually express it in that form. I think we are probably right. Yeah, you can see it has actually been done for you. So what you are removing is this gate and that gate, because they are inverters, and also this gate and that gate, and you remain with that gate and that gate. In fact, if we use the quad NAND, we end up with 2 gates, whereas here we were using 3 gates. So this is even simpler. But obviously, this you only do this if you've been asked to express it in NAND gates. Let me show you how. I don't remember. Yeah, they have said implement it using the 74HC00. This is CMOS. Quad 2 input NAND chip. So if you have a NAND chip, it means you only have NAND gates. And so that is indicative enough to say that actually I need to express my output in and use only NAND gates. Okay. Yeah, okay. So we can stop here. Next time we will do the kind of map method of simplifying digital logic circuits. But we have we'll end here. We'll meet again on Wednesday. If you haven't understood anything, we can do it. Yeah, we will stay online, Francis. We've already talked about this. We can, you can read through the material. I really cover a lot of material every time we meet. So please try and go through it. We should be doing an exam, a test in, yeah, we should be doing a test in about 2 weeks' time from today. And it will be physical. So please start reading if you have not yet been reading. Otherwise, have a nice day and see you again on Wednesday.